So again, my name is Mark Fretz. I'm at the University of Oregon. I co-direct the Institute for Health in the Built Environment together with Siobhan Rockcastle, Professor Rockcastle and Eugene. We think about health at multiple scales. The scales of microbes, which you'll hear about today, all the way up to the scales of communities and planets. So a lot of carbon and LCA, which you'll also hear about in this session. So with that, I know most of you, we've connected in some way on other projects, and it's really great to kind of bring some of these projects home today. Some of these are just starting out. Others have been going on for a while. So I am going to go ahead and start with a couple of projects that I've been working on together with others in the room. The first one is carbon narratives for design planning. Actually, and how do I forward these? I should have probably asked that. Thanks. Okay, carbon narratives for design planning. This is a project that has been going on since pre-COVID. In fact, we started this back before COVID as a project to start to think about all of the implications of carbon and structural materials. Our students were doing LCAs, whole building LCAs on projects and getting different results depending on the questions they were asking about biogenic carbon. So we heard from practitioners that there would be really a desire in the industry to know more about what these issues are and why do we have different narratives such as, well, all steel is recyclable or concrete sequesters carbon and it's, it's more durable, therefore better, or wood is all good. And so we started to dig into these issues in this project together with industry experts, with experts in academia and nonprofit and government. This was a project that Alison Kwok, Professor Alison Kwok, was a co-PI on at University of Oregon in her NetZ lab, as well as Quorum. But we had an amazing group of student researchers on this project. I have to give a special acknowledgement to the graduate student, Ethan Bloom, who did a tremendous amount of work on this project, did all the visuals, the graphics in the final document, which you can find online, and just really made this thing happen. In addition to Ethan, we had a really great series of speakers. So this project, like I said, started off with industry. We did a survey of industry initially to see what were some of the concerns they had, what were some of the questions they had. Not just industry, but also, like I said, nonprofits, academia, and educators. And we got over 300 responses back for the survey that informed a series of workshops. Initially, this was going to be one big, let's get everybody in the room workshop, and then COVID happened, and these things went online, which allowed us to do really some unique things. We could have speakers from around the world come talk and frame these workshops based on this document. So you can find these workshops on our website, buildhealth.uoregon.edu, also on the NetZ website. And the final document, which I would like to announce, is now ready for you to take a look at. It's out there, is also on our website. And I assume it's going to be on the Tallwood website soon if it isn't already. So please check it out. We'd love for you to take a look. It's like 100 and some pages, so all the transcripts from the workshops are in there, as well as a breakdown on these different structural materials. And it's done in a visual way that we hope architects can appreciate as well as others. It's already been rolled out in classes, so it's really exciting to have this project that Tallwood and the ARS grant funded. So some important takeaways for this project. Like I said, I could go on quite a while. It's a long document. We learned a lot. It was an amazing journey. And when we started this journey, we did this along with a lot of you in the room, and you've all been working on this and have produced some amazing work that's based on, the lessons that we're all learning about LCA and forestry. So this is by no means our work. This is everybody's work that we've really compiled based on literature reviews, and based on workshops with experts. So one of the takeaways is that buildings really are a big source of CO2 emissions. And I think most of us here can recognize that. We're all in the industry. But the global building stock is really burgeoning. We are increasing buildings at a tremendous rate, and it's expected to double by 2060. In fact, that's equal to about 1 New York City amount of floor area every day in terms of the built environment expansion. So we have a big role to play as professionals in this industry to help reduce that CO2 emissions from the materials that we select. The mass timber carbon story, and as has been mentioned in presentations earlier today, begins, well, with design and the selection of materials, but also the end of life and material reuse portion of this is really important. And that's why there's more effort right now going into that research, because what we do at the end of life with our materials really matters in terms of the carbon story. Designing for disassembly and reuse and how that's going to occur and how we get those materials into the market is still a work in progress in terms of the research and certainty around that. But we hope that with the other projects that are funded, we're going to know more soon. But that's an important part of the story. Transitioning to timber cities over time could reduce our carbon emissions by about 77% over business as usual, depending on the percentage of wood that we're using. So that was a paper that came out in 2022 from Mishra et al., and that was an interesting finding. But of course, it really depends on us managing those forests appropriately, doing good sustainable forestry practices, and protecting diversity hotspots around the world. So there's some caveats to that, but it's a good finding that this can be a good solution for our carbon emissions. This is a graphic. I mean, I hope you can see these. I guess they are a little washed out here, but Ethan Bloom did these, like I said, and they're beautiful to look at in our document. And this is, just talking about how mass timber can be important as a structural material for reducing built environment carbon emissions as we start to move that carbon pool into the built environment, and building durable buildings that last a long time. That's also really an important key to maintaining it in the built environment. Mass timber can be sustainable. Like I said, if forest management is sustainable, one of the things that we learned too is just really trying to use the entire harvested stem fiber for long-lived products, not just things like paper that might be short-lived, but really getting the mill waste, for instance, that happens when we make these products into other products that can be stored in the built environment for much longer periods of time to lock up that carbon. So that is the project. There's a lot more to it, and this is just an overview, but it's a document that I hope you can all dig into. Maybe with a glass of Pinot Noir, sit down and read it this weekend or something. It's done and it's out there and ready for you to look at. Another project that we're getting ready to launch, this one was funded this year by ARS, and I'm really excited about it. We don't yet have the contract signed at University of Oregon, so we haven't started, but it's coming very soon, is the infiltration of all wood construction techniques. So as we just talked about, it's important to build our cities more out of timber to get carbon out of the air. And as we want to do that, where do we put more wood fiber? Well, the enclosure is one area which is relatively untapped in this country anyway. In Europe, they've done some more projects with wood in the enclosure, but we really want to start to see projects where mass timber is going into those systems as well. We had the opportunity with a Wood Innovations grant to look at that on a beautiful project that's constructed and do a post-occupancy evaluation of the interior environment with all wood construction. So we looked at a number of things, but in particular, we were interested in the thermal aspects of that enclosure, especially since wood is a fairly good insulating material, and mass timber, the thickness we suspected could play a pretty good role in being a thermal barrier for the cladding attachments and everything on the exterior. So this project used infrared imaging to look at the enclosure, as well as blower door testing to look at infiltration, and then also imaging during the blower door tests. One big problem that we had when we go out in the field and do these tests is there are all kinds of other variables in the building when you start to pressurize and depressurize them that were not able to allow us to answer the question about how the mass panel mass timber panel joints were working for infiltration. There was a big roll-up door, for instance, and some other offices that couldn't be closed. So we tried to tape off an area where we could assess that. We tried to figure out a way where we could isolate a joint and just test a panel field area, but it's not easy to do. And so we got some good data from the infrared images that suggested the mass timber was a pretty good thermal barrier, but some of the weaker spots were at the joints for infiltration. So we suggested that it would be really great to study this in a lab setting and create an assembly where we could specifically isolate joints and look at joint configuration with a duct blaster in a sealed box configuration. So that's what we plan to do, an 8 by 8 foot field area with several mass timber panel joint configurations, which you probably can't see here on this, but we're going to be looking at 3-lam CLT as well as 4-inch MPP. And I know the project we looked at had some thicker wall assemblies. This is because we don't have an overhead crane at the University of Oregon. We have our backs that have to lift this stuff. So they're going to be a little thinner than what we tested. But the key is that we're going to be looking at a lap joint, a spline, and a butt joint with and without a sealant or a gasket. We don't know exactly yet what products we're going to use, and with and without a weather barrier. When you add all those up, you get 24 different tests of these things. So we could start to really get some quantitative data on this. And next year we'll be the ones maybe with a graph coming back here in the design section, which we don't have this year. So like I said, this one is just getting started. Hopefully very soon this fall. We've got students lined up to work on this. And the students, like Erica mentioned, we hope will one day go out into your firms. I should also mention that Ethan Bloom is now at FFA. So it's great to see the students that worked on these projects go out into the firms here and be part of this ecosystem. So I didn't keep myself honest with timing. I think I went over a couple of minutes. I'm going to call the next person up. And my colleague, Jason Stenson, is going to present more of the projects that are going on at IHBE. And Jason's been actually a big part of all of these projects.
So 4 projects. The first 2 are energy and seismic panelized retrofit projects, residential and commercial. And the last 2 are acoustic testing projects, material development, and assemblies for mass timber buildings. Starting with retrofits, you don't have to go too far from here to find a building typology like on the left. Looking at 2- and 3-story multifamily residential pre-1990s construction, pre-seismic and energy codes at that era, and built to the minimum code standard of whenever it was constructed. And looking at how we can put as much as we can into the facade for those retrofits. We have a lot of existing building stock. A lot of it is aging. Some of that at least needs to be a part of a low carbon, low energy, highly resilient future. And so that's what these projects are about. Part of that initial project was a small mock-up done at the Emerson lab. And to get from existing condition to retrofit facade, we looked at some of those details required and fabrication processes. One lesson learned in that process is related to scanning. So the concept here is that you would go out, take multiple LiDAR scans of an existing structure, translate that to 3-dimensional models, fabricate your panels, and hopefully they show up on site and they fit. Not all point cloud data is created equal, we've found from LiDAR scanners, and the workflow, digital workflow with that data is a critical piece, and we hope to implement that lesson learned and others in these current projects. So the first one is the evolution of that residential project. This will be built inside at Emerson, and we are just to the point where that drawing set is about complete, and to put that RFQ out for a contractor who will build both the existing and fabricate and install the retrofit. The interest here is really to layer on the reality of constructability and cost aspects for the project. So similar to the first small mock-up, this is a retrofit foundation tied back to the existing slab if it was a slab at grade, and that's where those seismic forces are resolved at. In the middle, you can only see the transfer joists that tie the existing structure at each floor diaphragm and roof diaphragm into vertically oriented, vertically spanning MPP panels in this case. And so we've done a lot of thermal and also moisture modeling. This is temperature only. This is a idealized case where temperature is held constant, warm temperature inside the building and cold temperature outside. And the simulation runs until the entire wall assembly has reached steady state. You can see that temperature point is right down the middle of our stud bay on the left. And by adding the MPP panel with inboard and outboard wood fiber insulation, we're able to move that transition temperature out of the existing structure. On the commercial side, this is an ARS funded project. We are partnered from the get-go with William Silva and Swinnerton. Looking at a case study, this is a case study project, not a mock-up, and finding a Pacific Northwest commercial office building that has been recently retrofitted, seismically retrofitted, though not with MPP energy and seismic panels, with those BRBs we've been hearing a lot about, earlier. So this project also is a replacement facade project and not leaving the existing facade in place. So we have some opportunities related to exposing mass timber on the interior, raising head heights of windows to get daylight further back into the space. So stay tuned for more on this project. Moving to mycelium, which actually there is growing research for thermal insulation of biocomposite products. Our interest here is in acoustic applications, using that in a floor ceiling assembly, for example. The mycelium is the binder, and so potentially that's replacing adhesives and other petroleum-based products. And the substrate can be wood waste from lumber mills or mass timber production. So that's the direction we're going with this one. Just getting started with it this fall, perfecting our recipe and procedure for making this mycelium, growing this mycelium. So there's an inoculation step with the mycelium and moisture content and incubation period. And to stop that growth, there's heat and drying at the end of that. So we hope to investigate both the material properties of these acoustic panels at a larger scale. We're going to test them for acoustic properties in our microacoustic chamber, and hopefully have an acoustic performing alternative that's a biocomposite. Why microacoustic chamber? First, this is an ASTM test facility, full-scale testing of mass timber assemblies. The assembly needs to be quite large, the test sample, and it is the partition between two large rooms, the source room and the receiving room. Our microacoustic chamber is much smaller, and it is just the receiving room. What that means is we can't accurately measure those long wavelength, low frequency sounds that are required of an ASTM test. However, we can do lots of tests quickly and cost and material efficiently. And this is really intended to provide comparative test results and development of materials like mycelium panels. Our microacoustic chamber has an inner and outer box and 6 inches of sand as our primary acoustic dampener between that. The mass is good, the interstitial air spaces are good. And the test sample sits on top of that box. We're using our field testing equipment, an omnidirectional speaker, and our tapping machine as sound source. And the lab itself is our source room for those. And the test sample is also surrounded by sand as a primary sound isolator. We have a donut, we call it, a plywood donut that goes on top, and all of those air gaps are sealed with putty. This is all time-intensive steps, and at this scale, it's much quicker. So we've most recently used this microacoustic chamber for REACT's consortium testing, and we've finished the first phase of that testing based around 5-lam CLT and interlayers and acoustic treatments that can be applied to that. So here's some time lapse of that. We now have a gantry crane in our Portland lab for lifting CLT samples and concrete topping slabs. Each assembly is sort of installed in this with the sand and the putty, and then tested both for airborne and impact sound. So one thing you'll see here in a second is we're also testing it with carpet and carpet plus carpet pad, and those were easy to do, and it gives us another 2 more data points. And unfortunately, nobody likes it, but carpet is a great acoustic treatment, specifically for impact, especially. So this is phase 1. The next phase will also use the microacoustic chamber and some lessons learned from this first phase, picking winners from the material categories. And then ultimately a smaller set of full-scale tests will be developed and conducted at an ASTM facility. So thanks.
Okay, thank you, Jason. Now Gerry Presley is going to come up and talk about some microbes at the smaller end of the scale.
Thank you very much. Oh, yeah. Perfect. All right, I'm Gerry Presley, Oregon State University Wood Science Department. Today I'll be giving you just a brief introduction into some of the things that we've been doing with a collaborative project with University of Oregon, looking at coatings and their impacts on mass timber surface microbiomes. So essentially this project is born out of the need to protect mass timber from moisture. One of the areas where this is particularly important is during construction. Photo here, many of you have probably already seen this, comes courtesy of Jeff Morrell during the construction of PV Hall over at Oregon State University. It just illustrates that you can get quite a lot of water flooding into floor assemblies during construction, and CLT and other mass timber products are large, and so they're more difficult to dry out once they get wet, and that can cause some issues for decay, durability, and the like. So there are several solutions out there that are increasingly being utilized. So tarping and putting up moisture barriers during construction, pre-installed vapor barriers on, or pre-installed membranes on mass timber panels in the factory to help prevent this wetting during construction are a couple of options. But another option that's out there is coating. So actually coating the surface of mass timber to decrease the wettability of the panels and reduce moisture intrusion. So some of the work done by University of Oregon shows that the microbiome on the surface of mass timber panels is actually really important, potentially important in modulating the health of the building inhabitants, and that could be one of the factors that contributes to this benefit we get from biophilic design. There's also some prior literature out there showing that coatings on CLT in particular for this study can actually interfere with some of the microorganisms that are that can potentially grow on mass timber. So this study particularly looked at defacing molds, and some of the coatings actually reduced mold growth, which is a good thing, but that's kind of an indicator that there may be some negative interactions with other microorganisms that grow naturally on wood surfaces that can be beneficial. And so that's one of the things we partnered with University of Oregon to take a look at with this study. So University of Oregon is doing the work to essentially assess the impact of several different coatings on the composition of microbes or microbial communities on CLT surfaces. And we got some of the same coated pieces of mass timber and assessed the coatings for antimicrobial activity to see, are we doing any harm by adding a coating to increase or decrease the likelihood of beneficial microorganisms from growing on the surfaces. So we did this by essentially taking some of these, they ended up being CLT rounds. Some of them were coated, some of them were not coated, and then shaving off the very outer surface, grinding it up, and then exposing bacterial cultures to this in test tubes as pictured on the left. And then we incubate them on a shaker and then measure essentially the growth curve of the bacteria and see how the wood plus coating interfere with bacterial growth or if at all. So what we found is we looked at 3 different bacteria, gram positive and 2 gram negative. So Bacillus subtilis is our gram positive, E. coli, Pseudomonas putida are gram negatives. We've got a variety of different coatings here, 3 different coatings, and then we also took the layer of wood underneath the coatings just to see what the effect of the wood itself is. And what we found is that for Bacillus subtilis and E. coli, coated Douglas fir CLT, we don't see any impact of the coatings or the wood, but we did see an impact on one of our bacterial species that we tested. So everything except for the wood-free control did not grow very well. So this indicates to us that the coatings really aren't causing an issue, but the wood itself has a little bit of antimicrobial activity for that specific bacteria. And this is also supportive of some of the work that U of O has done in the past, in that wood surfaces kind of have are able to modulate their own microflora. So you can say this one type of bacteria is not going to grow very well on wood surfaces, and other bacteria may grow well on wood surfaces. We also had SPF CLT in the study, very similar patterns, maybe a little bit less antimicrobial activity for our Pseudomonas as compared to the Douglas fir CLT. But again, not a whole lot going on for the coatings. So again, at least with our methodologies here, we did not see any impacts of the different coating or any antimicrobial impacts of the coatings. The wood does have some antimicrobial activity against certain bacteria. And one caveat to this data is that our assay may not be to the sensitivity that you need to pick up on these small changes. So for example, we are trying to get as much of the coating in these microcosms as possible, but the vast majority of the material that the bacteria are exposed to is actually the wood. So that could be just a factor we won't be able to detect in this specific assay. So U of O is working on getting some data on what the actual composition of the microbial communities are on these differentially coated surfaces, and that may tell us a different story than we've found with our assay. So with that, I would like to thank TDI, USDA ARS, and collaborators at U of O. And thanks. Take any questions. Yep. Was that good timing?
Perfect.
Yeah.
Yeah. Yeah, I think we'll have time for questions at the end. Just looking at how we're going, we should be good. So I hope you hold those. We still have some great presentations. So speaking of which, my colleague Judith Sheine is going to talk about 2 of the projects that she mentioned earlier, I guess. Yeah.
At least one of which.
Green button.
Yeah, thank you. So I'm now speaking as professor of architecture from the University of Oregon, you know, still part of TDI. And I'm going to talk about a couple of projects, one of which you should probably already be familiar with. And I'm about to apologize because I have a couple of slides later. I think none of these slides are going to be visible given the light situation, but I'll talk through them. So I think everybody is aware, probably everybody in this audience, that we've been working for a while on developing a prototype for mass plywood housing. And specifically the prototype is for little 2-story ADUs, accessory dwelling units, or for cottage clusters, you know, with the idea that real estate is one of the most expensive pieces of housing. Oregon has just, you know, changed zoning laws, and well, they haven't changed the zoning laws. What they've done is gotten rid of single family zoning in any city over a population of 10,000. And they're asking cities to change their zoning laws to allow much denser development. So we decided to look at this specific type and see if we could make it affordable, meaning that we don't expect it to be less expensive than lightwood frame, but we're hoping that it can be equivalent with prefabrication and have all the co-benefits we talked about when we talked about the Oregon Mass Timber Coalition and the EDA, that we encourage selective harvesting, sustainable forest management, wildfire reduction, more jobs in rural communities, manufacturing, et cetera, and that we would create something that is actually a better product, meaning that it's more thermally resilient, more seismically resilient, and more fire resistant than lightwood frame. So as we said, and I've already shown you this slide, and this will be the last of my slides that's visible, I'm pretty sure, that we went with a panelized approach, so that the idea is that it could be done in a factory, but we're also designing it at small enough scale that a contractor could just get the panels pre-cut at Ferreras and then do everything else essentially in a warehouse without very fancy tools and equipment. And these are very vaguely visible. Anyway, so I think everybody knows that expression that you can either do things fast or cheap. We are not doing this fast, I think would be fair to say. We, and by we, Mark Fretz and Jason Stenson, have been working on this for like 3 years now. Why does it take us 3 years to design a very small house, especially when one of my specializations is supposed to be housing? Well, it's because nothing about it is like a lightwood frame house. Everything is exposed, including all the services. We're trying to figure out how we can actually make sure that jurisdictions, building officials will accept this, because as I was just discussing with somebody, nothing about this is in anybody's code that you can have a 2-story building out of 2 and 3-inch mass plywood panels. So it's taken us a while to figure out how to do this. We hope to actually really start construction on the first prototype inside Emerson. We're very excited that we'll be doing this inside rather than outside. And we hope to be starting construction at least by the end of the fall term. We tend to measure things in quarter terms. Fall term, and be well underway by winter. We're doing 2 prototypes. And again, it's a tiny little 2-bedroom, under 800 square feet. 2 bedrooms on the upper floor, bathroom and a half. These are the exciting elevations. We've been working on, obviously, what the assembly for it would be. We're waiting for Timber HB to come out with their hardboard wood fiber insulation. They won't have it in time for our first prototype, but this prototype, we're going to be doing structural testing and constructability testing. Once we think we know what we're doing, we're going to have a second prototype, which we're actually going to construct outside. We're going to have a contractor do that to tile in on costs. We think that the wood fiber insulation will be ready, produced in the US by then, which we want to use. And outside we'll be doing acoustic, thermal, probably indoor air quality tests, and encouraging our TDI staff to hang out in there and have meetings so they can generate some moisture and germs and all kinds of stuff that we can then measure. This is, just some details we've been working on. I really put this in to show that we've made progress from last year. That's really the point of these images. And we're particularly, dialing in on exactly which panels we're using. We've laid all these out on 3-inch panels and 2-inch panels. We're trying to waste as little as possible. We're kind of entertained when we realized that our framing plan had virtually no framing in it. It's basically just panels. As you can see, the panels are all specified. We have actually layouts of files that we're about to give to Mark Gehrig, who is sitting in the back, first to have him look over and make sure that they make sense, and then eventually to fabricate and put on the floor. And we're excited that we've gotten this far. And I know there's been a huge amount of interest in this project, and we hope that once we get something going, we're going to put some things on our website where people can sign up for tours. And we hope we have a successful project, meaning that we hope that it is actually affordable, it can compete with lightwood frame, and we can get some developers to actually build it. All the information will be open source because, of course, it's funded publicly, mostly by this EDA grant. So I thought that was the last slide, but this is the last slide in this, again, just showing all the panels that we're using and the cuts that we're making. And get another one. I'm trying to get the next one up, which doesn't seem to be coming, which is the reuse one. I seem to be stuck again. No, went way too far. Can we go back several? Nope. We seem to be skipping one. Let's try. There we go. I think we're good. Okay, so this is a completely different project. This is the reuse project. And I think the last time we did this a year ago, you saw the Ellie project in about 4 different presentations, which you're also going to see today. So as you know, this was a project to test a number of structural issues. I was interested in seeing what we could do with it when it was deconstructed. And it seemed a little bit crazy to me that this stuff would go to landfill and that we could possibly find a way to reuse all the parts. And I think the LCA is showing that landfill is better only because the data in the LCA is based on lightwood frame construction. It has absolutely nothing to do with, reuse of mass timber. So this is not typical reuse. Obviously, this is not a real building. It's a test, but I still thought that it would be great to find a way to reuse it. So one of my MS Master of Science students last year, Amanda Stanton, did a kind of analysis of what could be left over after all the really big steel connections were cut off, and what would be left of the 7 1/4 inch mass plywood decking, which Andre projected would be undamaged for the most part and could be reused in something. And she also cataloged all the steel pieces as well. So the next step was to find somebody who would actually use the stuff in some way. I say, looking at Jonathan Hepner, who's in the audience, is I talked to Lever because they're willing to do all sorts of crazy things. And we started talking about what they might do. So it turns out there is a project for the University of Oregon, which is now slowly moving into the former Concordia campus. And Lever is renovating a former theater there into what will be the architecture department for U of O. So we discovered that they were interested in maybe using some of the panels from the Ellie. Now, we could not use them in a structural use, as Maria Paula has talked about, as Andre pointed out to me. The issue is there's no recertification process yet for used mass timber panels. Not only that, but we had a kind of fantasy as architects that you could just cut these up and turn them into columns and beams, but that doesn't really make sense. When FERS makes them out of columns and beams, they know exactly where all the seams are, and when you just cut them up, you don't. So there's another of limitations in that. But nevertheless, we did manage to find some non-structural uses for them. And here is an image of the Ellie coming down and creating giant piles of 7 1/4 inch MPP. at the alley, and also big piles of steel connections, some of which have actually been used by others, which we're kind of very excited about. And then Mark Gehrig has been working out a protocol for, modeling and cutting these things up and on our CNC machine, on our BSA. And you can see, we have stacks of these that are cut and fabricated and labeled. And eventually they're going to look like this. Even though, as I pointed out, I think this looks a little nicer than our MPP, very used MPP is going to look. It's going to have stamps and a few holes on it in places where we took out straps. But still, it's going in an architecture studio, so we're very excited about it. It's going in to define the low walls around the studio spaces, and also to define these volumes that will be the conference rooms. So we have somehow I didn't get the cut files in here, which would have been unreadable anyway, as we know with this land shift. But Lever sent Flynn Casey, one of our former UO architecture students, did a set of files for what they needed cut, sent it to Mark, who has modeled it and is cutting it. And these files, the panels will soon be shipped to some place for storage until Lever is ready to use them. So we're thinking of this as a case study of all the things you can do, the things you can't do, the limitations, especially the structural ones. And we hope to be able to, when this process is done, disseminate it and publish it on our website. Thank you. Was I under time?
Yeah, perfect. Thank you, Judith. Okay, great. Like to welcome Cory Olson up to the front. There you are, Cory.
Thank you. So actually picking right off of Judith's work, when Judith has scraps that she doesn't want, I get those scraps. So I'm an interior architecture professor at University of Oregon, and I actually did this also with my co-PI, Linda Zimmer. Linda's on her way to Chicago right now for an accreditation visit. But what we were looking at was mass timber scraps. And we had a premise coming in not as people involved in mass timber, that those panels, in the processing of those panels for architectural jobs, are generating cutouts, are generating panel ends, trims, and nesting. So through various interviews, we found that to mostly be true. And those scraps were actually most commonly either going into cogen, getting chipped up and turned into energy, going into landfill, or going into long-term storage with like this indeterminate, we might use that someday. So what we are proposing is a series of prototypes, ideally that would be made at the factories as they're processing those panels. So this whole idea is an open source platform of, we design furniture, we prototype them once as a proof of concept, and then hopefully we've talked to panel producers to see if there's something that we might be able to work into their process, both to help the sustainability story, but also the material circularity. So if you've been coming to these symposiums the past few years, you've seen some of our work, but I'm going to show you two of our newest ones. So this also illustrates kind of our evolution of understanding how the CNC processes work with panels. So the first one is kind of what we call the suitcase. So some early renderings. What's cool about this is it can all be cut with a circular blade on the panel CNC. There's no tool changes. You can make this modular from an 18-inch individual seat all the way up to a 40-foot long bench if you really wanted to. So just with some pretty simple, not off the shelf, but very easy to make steel pieces, you can make this seat. And then we've made kind of that 18-inch version. We've also now made a kind of 5-foot version that Phil actually helped us cut out. That got installed at the UO Fuller Land Lab for a couple weeks as part of an exhibition. And it's now got a semi-permanent home at the Oregon State campus. And we're actually doing that to also see how it weathers in outdoor environments, to see if these are assemblies that can be durable for a long-term period. Another one that we just assembled is something that we've dubbed the tete-a-tete. So I work at the interior scale, former cabinet maker, former furniture maker, or I suppose current furniture maker. But the tete-a-tete is actually a historical form type, which is also known as a gossip chair. where people in high society could sit together and basically gossip without looking at each other. You're just kind of like throwing comments over your shoulder. So this one we've got parts for two. We've put one together, and now we're exploring where we might actually do an installation on the UO campus. But particularly for students, you might not want to share a small piece of public furniture with someone, but this one actually gives you kind of your own private realm. So one person can sit on one side. If you want to talk smack about someone, you still can. Or if you want to have kind of your own world, you're on your own side. And then I thought I would throw in a few that we've already presented to this audience before, but the squall here on the left, this is actually a stack lamination of 3-ply CLT. And then we actually milled that using the KUKA robotic arm at the Emerson lab. And then on the right-hand side is one that we're still kind of in the wings. We've got the facet table, which just kind of works off of this 15-degree bevel. The Mesa bench, which is again a modular piece that's also scalable. So this is something that could be a standalone, or if you actually produce them in multiples, they can go together in different arrangements. So you can have a linear arrangement, a 90-degree arrangement, a 120-degree arrangement. So it actually turns into like really effective public furniture that complements the scale of mass timber material. And then we've got the Tory bench. So the Tory, we actually explored this idea of partnering with a manufacturer. So DR Johnson, Levi helped us actually make and build 2 of these. They made them in-house and constructed them in-house. So the Tory just worked off of this pretty simple kind of Japanese joinery style. And then again, something that can be scalable. So we made a 6-foot bench, but again, this could be a 12-foot bench. For the weight of a human, you're not going to get massive deflection over a few people sitting on a bench. So we were just kind of curious to see, again, in exploring these prototypes, what could actually go into a production process. It's been pretty well received. So we've actually shown it in Canada, we've shown it in Norway, we've shown it multiple times in the US. So we've gotten some good traction and some good interest, both in kind of the engineers realm as well as the public realm. And really what we're looking for now is getting those connections to panel manufacturers. So particularly in this audience, if you know any sustainability engineers or plant managers that are looking to optimize their processes, or perhaps plant managers that are sick of storing mass timber everywhere, we would love to talk to some of those individuals to see if there would be an opportunity to share those files. They could explore in their own setups how to incorporate that into their mill line, and then see if those pieces could actually become either value adds, independent pieces that they sell themselves, or things that you get to basically give the clients because they've already purchased the panel. So this was actually a 2021 ARS grant, I believe, and then we extended it 2 or 3 times because of COVID. But we've actually just submitted our final paperwork this week. So we're excited about that. We've had a lot of fun, and we're excited to continue this work even if the grant has expired. So thank you very much.
Thank you, Cory. Yeah, it's a great example of adding value to the mass timber ecosystem, so really appreciate it. The next presenter, Dylan Wood, joined the UO faculty a year ago. So it's really exciting to see this whole ecosystem even expand within the University of Oregon. So I'm excited to turn it over to Dylan.
Great, thanks a lot. So I'm nearly losing my voice, so stay with me, but so it won't be too long. So I'm really lucky that after only joining less than a year ago, to be part of 2 ARS projects through TDI, one that I'm going to explain now and one with Erica Fischer, which will come up next. So the first one is called Next Generation Flat Pack and Deployable Wood Building Components. And this is a sort of very future looking project that continues some of my previous work, which is based off this very simple idea that we can create panels that start out completely flat, like what you see on the left. And then when you open up the packages, these will shape out to take on a 3-dimensional curve shape, which can add structure, but also ribs for putting services into later. And as I said, this is based off of some slightly larger scale work that I did already at the University of Stuttgart in my PhD and postdoc, where we used a similar process which uses the hygromorphic properties of wood to shape really large scale lamellas for CLT construction. That was then implemented in the Urbach Tower project at sort of load-bearing, full, partially certified scale. And that's a project that we continue now with Blumer Lehmann AG in Gosau in Switzerland to be implemented for like sort of full certification for producing large-scale curved CLT through a sort of shaping process that happens in the factory. So, and then also we've recently completed another project which uses this sort of deployability idea, again at a really large scale with a project called Hygro Shell, which is now on display in Chicago at the Architecture Biennale, where we have, again, these flat panels, which you can see here start out flat and vertical, and then over a couple of days shape out to form this sort of curved shell. And then similar concept we applied already to furniture. So this is like the easiest to understand, that you sort of get your IKEA furniture as a flat sheet that you see here, and then over a couple of nights it shapes out into the full form. So the question, or like the sort of start for the current project, is to look at how we might do that using slightly different material, more precisely 1/8-inch Douglas fir peeled veneer, which would hopefully come from Freres, which is we haven't used before in this sort of self-shaping exercises, but is particularly well suited because it comes already or we wouldn't need to dry it, so it comes already wet. And it also is like sort of continuously tangentially cut or peeled, which means that it has like an incredibly high expansion and swelling, or sorry, shrinking and swelling coefficient, which is ideal for what we want to do. And then what we will look at is how we can use that to generate cylindrical forms, which are of course valuable structurally. And then we will look at how we can apply it on a more timber or mass timber product basis, looking at flat floor panels or wall panels that would then have these curved structural elements kind of popping out of them. So this explains, we haven't started the project yet, but this explains how we're going to go about it. So we can use relatively standard veneers, and what my team will do at UO is to calculate and figure out the buildups that we need to glue up specifically in order to generate this self-shaping behavior. And then we're also looking at how to utilize the curvature in those ribs or in these sort of extra features structurally, with the goal being that if we go back, that we can sort of overall reduce the number of lamellas that we need in a panel by using the geometry of these curved elements to add structure. And there's also, of course, a lot of other interesting architectural uses, like if these curved surfaces can benefit acoustics, or if they could be used for mechanical surfaces that would come after that. So yeah, these are the expected results. We're going to build a full-scale prototype by the end of it. And there's a couple of like really interesting aspects in the sort of self-shaping realm that we will get from this by using the veneer, which is really seems really promising. And then I also just wanted to highlight that I don't show the students here, but we already integrate this sort of through research-driven teaching in the design studio environment at UO through a couple of projects that look at kind of how we can use curvature and thin elements for a kind of ultralight construction, which of course doesn't consider fire constraints, but is interesting to look at because it uses so little material compared to these sort of standard mass ply panels. Yeah, and part of this, we're also setting up a new physical laboratory at UO, which will be integrated with architecture students, and a couple of friendly robots in order to try to push and advance the digital fabrication aspects compared with and sort of in relation to timber with architecture and design students. So, thanks.
Thank you, Dylan. Okay, and to round out this last session, Erica Fischer is going to come talk. Thank you, Erica.
All right, I'll go quick so we can get to happy hour. So this project is working with Dylan Wood again on these curved surfaces, and really what this is we have the possibility of creating these beautiful curved surfaces with mass timber. But as we create them, this is an iterative process, and so how do we automate the interaction between the architectural modeling software and structural engineering analysis software? So as the architects continuously update their curved surfaces, we can, as structural engineers, continuously analyze them without creating brand new models every single time. And so what this is developing a framework to couple the architectural parametric modeling with structural finite element software, so we can actually analyze these curved surfaces. And so it is also, since we are both, I guess I'm not new anymore, but newer faculty, we were also talking a lot about how, you've heard a lot of presentations today about collaboration between Oregon State University and University of Oregon. And so we really wanted to explore, how do we dually mentor engineering students and architectural students as an engineering faculty and as an architectural faculty. So the way this is working, the project started this fall, but we already have some results that I'll show you, is that the architectural curves are modeled in Rhino and Grasshopper, and then using Python, we're able to actually pull the geometry out of Grasshopper and create an Abacus input model that has that same geometry. And so what we are hoping to do is become more complex with the curves, add in the ability to write our finite element models, input files using material properties and different boundary conditions, incorporate connections within there, and see how far we can get with this. That is it. Yeah, nice and short.